Whereas mode C is like delamination, breakage across multiple rows, delamination, breakage across multiple rows. So those were the three modes of failure that we saw pertaining to, I think, the W orientation more so. And generally, the combination, when we look at our flat samples, this is an image at room temperature. Generally, a combination of delamination and coating breakage is what we saw here. So modes B and C. And more breakage was seen at higher temperatures. The higher temperatures also resulted in more breakage specifically at the interface. It was more prone to fracture. The failure in the H orientation was modes A, B, and C is not applicable, but the failure was dominated by delamination at the interface. So while the room temperature and 100 degrees Celsius were actually, those results were actually similar, the 250 degrees samples showed large degrees of separation. So I guess the difference in thermal expansion affects this particular orientation at higher temperatures a lot more. And we can actually see that. So this is the A356H. At room temperature, you can see it's a little bit, the scale is a little different, but there's a little bit of separation. But at 250 degrees, it becomes quite prominent here for the A356H. Yeah, so that's all that I was going to share today. We do have a paper published that summarizes part A of our findings. That would be the microstructure portion. And we're currently working on papers for the pull test, the quasi-static bending, and then the cyclic bending. And I think Deval is working on the fretting fatigue testing right now. Okay. Thanks for the clap.
Thank you. Thank you very much, Jessica. It was a very nice and interesting presentation. I think it had a very nice flow and also visually very appealing.
Thanks.
Okay, if there is any questions, I myself have a few questions, but my knowledge in coating is very narrow. So I will wait to see other questions. I might get my answers through other people's questions. So if there is any questions.
Sure, I'll ask a question.
Sure.
Great presentation, by the way, Jessica. Very interesting. Just want to echo what Arfan said. I have kind of a more philosophical, high-level question. It seems like a lot of the effort you have invested here is optimizing a combination of the mechanical interlocking, so the strength kind of, let's say, counteracting the lamination of the coating. And there's two parts of that. Seems like it's mechanical interlocking, so like a mechanical attachment, and then a chemical bonding. Can you kind of speak to which one's more important in which situation? And maybe this might be hard to distill down to a percentage, but is there a percentage of the total bond strength that comes from the mechanical part and the chemical part? Is it simple enough to look at it like that, or is it a lot more complex?
That is a good question. I think our original goal from the, at least the adhesion portion with the comparison between the finite elements and our experimental results was kind of to be able to subtract the mechanical interlocking that we saw in the model from the experimental results. But we also saw in our TM study that we weren't able to identify any sort of intermetallics. So at this point, I think we have generally stated that the, as you said, chemical or intermetallics either have not been identified or do not play that large of a role, or they're just very tricky for us to be able to decipher using what we hoped was kind of a superposition method or a subtraction method there. But yeah, we have gotten suggestions to do another TEM study However, at a smaller scale, but I don't know how possible that is because of the budget constraint, I think. Yeah.
Yeah, thanks. That answers my question. I guess from someone who's not familiar with coatings, like Erfan mentioned, maybe this is a foolish question, but do you think that the lack of intermetallic strength is specific to the coating you're dealing with, or does this apply more to this type of coating system in general?
I think it more so applies to our particular samples because in thermal spray we have seen a variety of intermetallics present, which is why we were hoping to see something of the sort because I guess intermetallic bonding is very effective if we are able to achieve it compared to the mechanical. So I do think it is pertaining to these samples. Some people have suggested they have found it in similar samples, but we have yet to. But it is very, I guess, highly desired, in my opinion.
Great. Yeah, I think if it was easy enough to just spray the coating on and have it chemically bond, they wouldn't invest all the energy in mechanically bonding it. So it seems like it's there for a reason. That's good to know. Thank you.
Okay, let me ask one of my questions.
Sure.
You mentioned that for one of your samples that where this fracture initiate and what is the path of that. For different interlocking patterns that you have, is that different or they show the same kind of initiation of crack and fracture?
I think sorry. Yeah.
I think what I mentioned was slide number 32, around that slide. Or maybe you know better. Maybe you have that information somewhere else.
Oh yeah, so this is for adhesion. I think for when we're talking about the fracture path for bending or adhesion. Anyways, regarding for bending, I can answer that. When we did this preliminary study, all these samples were the dovetail pattern. But then when we did the second study, all of them were that wave pattern. So it's more so depending on the orientation. So the failure path for these two was slightly less. It was very similar for both the patterns, but in the W orientation, whereas the H is different. One thing that we did notice in our tests, our initial tests, was that there was a lot of like, there was a lot of breakage at the interface, specifically at these horizontal sidewalls, and we were really interested in seeing why that was. And when I think Dalal actually looked at it using SEM, he saw a multitude of, or a huge layer of resolidified particles that we weren't able to see because we were previously viewing it at this angle, just right there. So it really affected the amount of effective bonding that we can get in this pattern. So I guess that would be the main difference between the two patterns. The failure path, not so much, but kind of the reason why it initiates here at the interface.
Oh, geez.
So what you mean is that the orientation is more important than the type of pattern, right?
Yeah, in terms of affecting the failure mode.
Yes.
Okay, thank you.
I never want to see that vote again.
Because this pattern still has these kind of similar vertical sections.
Okay, it's Dalal.
Okay, yeah. Actually, I have a couple of suggestions. That's all.
Expert in coating.
I know quite a lot actually about this project. I'm involved in this project from the beginning.
Here's the thanks.
And yeah, so just a couple of suggestions, and then probably I'll just give some information to Andrew's question. So whether actually the intermetallic is playing a role here. For general question, actually, I have maybe in your introduction, somewhere actually, if I'm not from this background, maybe I'm missing what is actually the PTWA coating deposition method. Maybe if you can just show and where is the interlock pattern in the cylinder.
Yes, okay.
And what is the orientation of the interlock pattern? Because I know actually You are talking about
Would we have any
an age
small
orientation,
like
but
this,
if you are
Andre?
not in this background, then it will be
Countersunk.
hard.
I don't know what that
Yes.
is.
Proves what you're talking about. It's really hard to understand. And for your microstructural part, you use like different pattern than your full test, and
Yes.
and your flat sample. Probably you can highlight why actually you have done this study on this sample, then rest of the thing actually have done on the other sample. Okay. Or maybe if it's possible, just to use one kind of interface pattern to show the microstructure, some feature, and then actually move into your full test and then 3-point bending test. And also probably you can highlight the oxide is present in the coating is not like actually is not degrading the mechanical properties of the coating, because oxide is needed in the coating and it giving the higher strength of the coating, like actually higher hardness. Okay, so
Yes.
some of us actually we think if oxide is present in the coating, it's actually making the coating worse, or maybe it's degrading the coating strength, but basically not. Actually here actually oxide is needed to enhance the like actually the hardness of the coating to have better tribological property. Okay.
Sure. Yeah, that's really important to mention. I guess I didn't mention that the steel really does contribute to the strength of the coating, but it kind of does affect the failure modes that we see.
Yeah, and to just to add on Andrew's question, to add something, actually there is some intermetallic is present based on actually our discussion with our industry partner, because there is a nano layer intermetallic is present. They suspect maybe in the order of 5 nanometer. Okay, but when actually we initially actually started the TM investigation, actually we didn't look into that nano level of the interface, but rather actually we look into maybe instead of 5 nanometer, maybe 500 nanometer we look into. So we didn't actually find any kind of trace of intermetallic. Maybe intermetallic layer was very in nanometer scale. That's one. And what actually to identify what is the effect of the intermetallics or a metallurgical bonding from the mechanical interlocking, we did the simulation, and we found the simulation result is quite actually matching with our experimental data, which kind of suggests maybe by only mechanical interlocking we can have the strength we are obtaining from the full test. And although actually if there is any intermediate layer is present, that has very minimum actually maybe influence on the total strength of the coating. But obviously actually that is present. We can say that is obviously there will be present of nano layer intermetallic compound at the interface. Yeah.
Yeah, and I would also add that during our adhesion study, since we were able to view our samples from the fracture surface, we can also see the surface of the coating. And we found a kind of strange webbed texture, and Dalal did do a little bit of a study on that to see if it does have the potential to be an intermetallic, though
Smaller than 632.
we're not so confident about that, so we cannot claim it as of yet. So.
Okay, don't worry about it.
That's all from my side.
Oh, okay, perfect.
Or like a watch or eyeglasses or something.
Yeah. Okay. Don't worry. Thank you.
Okay, I also have another question. Can you go to your slide 38? Yeah, here for this red one, A319W, between 150 and 250, it seems that that's the only one that dramatically decreases its mechanical properties, if I'm not wrong. It seems that that is kind of affected by the temperature a lot compared to the other one. Is there any explanation for that? Did you find anything like why that happens?
We actually did see in some properties that the trends at 150, it didn't really follow like a successive from room temperature 150 to 250, but we are not quite sure yet why. We are also taking a look at, I guess, the differences between the testing. As you see, we had to use different test machines for, unfortunately, the room temperature we did using the 2 instrons, and then for the higher temperatures we used MTS for these 2. So I guess the trends, there's, although you've noticed that the 150 doesn't quite fall in place between the room temperature and the 250.
Yeah, that's also
Yeah.
correct. Yeah, that also. And the system is only aluminum and iron, right? So the okay. So I don't think there is any intermetallic in this system that might be, for example, stable on 150 and not stable on 250. Any intermetallics would be stable until like 600. So,
yeah, 250 is quite low.
Thank you.
Thanks, Jessica, for the very nice presentation. May I have some questions and comments?
Sure.
First, some editorial or maybe formatting comments. I'm sure that you will add that in your final version of your presentation, but anyways, maybe an outline up front and a conclusion slide toward the end of your presentation might be useful or maybe necessary. And the flow map at the bottom of your slide does not match with the slide subject. I'm sure that you will fix that in your final version anyways. And the other, apart from those comments, my other comment is that I didn't see too much information about the literature in your presentation. In slide number 4 to 6, I saw some just statements, but you didn't go through those. I think I think the audience or your examiners would expect you to show that you are aware of what has been done in the literature and what conclusions they have made through the research that they have done. So you can present those in your earlier slides, or where you actually present your own results regarding the microstructure, intermetallics, residual stress, or other things that you, when you present those, you can just point out what's available in the literature regarding those topics. I'm just saying that I couldn't find that information to the extent that I was expecting to see. And the other comment is that, in your presentation, actually, I couldn't understand how the Anton Par equipment works for the quasi-static properties of the coating. But could not this be?
So
yeah.
So for the
So this was for obtaining the quasi-static property of the coating only, right? Like not the like interlocking between the coating and the substrate.
No, it was just used for the properties as well as the hardness, using different indenters.
Okay, so the indentation, like the nano indentation equipment that we have here at UW, couldn't that be an alternative for doing this experiment?
Yeah, so we did try that. I was working with It was a very long time ago. I don't remember his name, but he mainly works with the cyclic indentation machine that we have here, and he was coming up with a way to transfer the results to stress strain curves. But while we were working together, it was kind of like a development process, and we both had codes for it, and we were trying it out. But the professor was sending off these samples to Anton Parr that had a sophisticated method in place already, so that's why we did this. But we did try on our own to implement. I think I have a couple slides. So the equation, we try to implement something similar to read our data.
Okay, I see. So I think his Abdul Basit, yeah, that you worked with. Anyway, yeah. So and one very basic question, maybe. I'm sorry if that is very basic, but to my understanding, cylinder bore, which is the application of what you're doing in this research, is under compressive stress from the piston ring and from the gas combustion that is happening inside the cylinder. So then my question is, why adhesion or interlocking under tensile load is of your interest, while we know that this component is going to be under compressive?
Yeah, I think we're more so interested at this point. Of course, that type of testing is also necessary, and we also have fretting testing. We're most so interested in the bond strength, kind of putting a specification on that for the coating and the various variables that we can change, like the materials and the interface pattern. Yeah. So yes, a little bit, how do I say, removed from the particular application. It's more so just finding the bond strength of the coating.
Okay. Yeah, I thought maybe corrosion resistant would be more important, probably, like just application wise. But yeah, I understand what you're saying. Okay, yeah, thanks for your comments.
Yeah, I think the fretting actually, in terms of wear, is probably the most relevant in terms of the particular application.
Yes, exactly. Yeah. Yes, I know that Dulal is working on that. Yes. Yeah, thank you very much. I'm done.
Thank you.
I think Dulal has a question or some clarification.
Yeah, actually, yeah, just a clarification actually. So about this Anton Parr result, actually how actually it works, it uses actually a spherical indenter, like it's a cyclic spherical indenter with a very low load, like 20 micronewton or micronewton, and then actually it actually did cyclic indentation on the same spot to determine the amount of material actually it's the impression of the amount of material under that actual ball indenter, spherical indenter. And then using some empirical equation, actually they estimate what is the strength, like actually the mostly the elastic and plastic deformation, mostly the plastic deformation within the volume of the material. And then it can represent, it can actually produce a representative stress strain curve, which kind of actually represent the local property of that material. Okay, so as our coating thickness is around 200 micron, we cannot actually produce any kind of maybe micron size sample or sub-size sample for real tensile testing. That's why actually in order to have the property like actually yield strength and also the elastic modulus of the coating, so we did cyclic indentation here. And before actually we match this elastic modulus for the coating and substrate with the other material, like actually on the magnesium substrate, like here. In this slide, actually I'm showing here actually showing the Anton Parr spherical actual cyclic indentation modulus of elasticity for, I think it's for AZ80 material. and then Barkovitz indenter, that is the nano indentations, triangular nano indenter, and then the bulk sample. So where actually we are seeing the similar kind of elastic modulus we are achieving using this cyclic or spherical indenter. That's why actually we use this method to determine the Young modulus mostly on the coding, because that actually Young modulus is required to estimate the properties of the coding that actually Jessica used for I think abacus simulation and other calculation as well. That's why actually we did. So this curve here actually showing the strain curve is like actually the representative of the stress strain curve. You cannot actually compare with the bulk sample stress strain curve, but it will actually give you some representative. I cannot actually tell like how actually representative stress strain curve is different than the real tensile test, but actually you cannot compare the value actually you are having after plastic deformation. Actually you cannot compare, but within this elastic region actually you can have the better estimate of the property.
Yeah. Oh, and I wanted just to mention as a fun fact, the reason we had to resort to Anton Parr is that we did try to use very small tensile samples of just the coating extracted from our samples. I think those samples were maybe, I don't remember, 2 centimeters in length. And we went to the lab, I don't remember which professor, but he does tensile tests on bone specimen. And we did try to test that out, but the coating only samples were very fragile. If you placed it on the table incorrectly, it would break. So yeah, that's why we had to resort.
There is no other way actually we can estimate the coating property, because coating was only maybe 200 microns thick, and there was a lot of actual porosity and other defect in the coating. It's very brittle, so we cannot actually load in any other way to estimate the properties of the coating.
Okay, thank you, Donald, for this clarifications. And as a follow-up on the editorial comments that Behzad provided, I think the presentation might benefit from just one slide describing the process itself. I know that you did a lot of things and you don't have enough time, I think, to present all of them. But for like someone like me, I learned about this process throughout the presentation. It was at the middle of the presentation that I found out that, for example, there is this interlocking effect that I was thinking about more metallurgical kind of bonding. But I think one slide might be nice to have to talk about.
Oh yes, so yeah, for sure. The literature needs to be a little bit more clear, as well as the process, and for sure showing the work that's been done to determine these interlocking patterns, which I've realized I missed.
But the flow is very nice, and everything it was very nice.
Jessica, regarding the question that Behzad asked about compressive stresses, so I mean, what is the state of stress on this coating when a cylinder being pressurized? So what would be the main stress on the coating and the interface?
Oh, I was under the impression that would be very similar to what we are simulating in our fretting tests.
Yeah, apart from the fretting part, which has to do bringing in the friction between cylinder, bore, and piston. But when cylinder is pressurized from inside, what would be the sense of the hoop stress that is induced in the cylinder? So if you consider a cylinder under internal pressure, right? You would have some hoop stresses, you would have radial stresses, and you could have also longitudinal stresses. mainly due to changes in temperature. But the main stress, or the largest stress, is the hoof stress. What would be the sense of, when you pressurize it, would you expect that cylinder to expand?
Yes.
And would that not create a tensile hoof stress at the bore or close to the bore?
Yes, but is that related to
a
tensile pull test?
So your bend test had the coat under tension, right?
Yes.
The way you test it, you put the coating on the other side, opposed to where you're applying load. So it would be under tension. So somehow it mimics.
Yes, the bending, but
yeah.
Does the adhesion test?
The adhesion test, adhesion test is a pretty standard test. ASTM standard for finding the pool adhesion. It's called pool adhesion. You can also do scratch test, which is another test regarding the, again, adhesion on the shear mode. So those are actually for quantifying the strength of bonding, which is kind of irrespective of the actual loading case that you have. It's just a measure of the quality of the bond. So if you have, for example, Kamau, and then you have Kyocera, or you have this PTWA versus another thermal spray or even cold spray, how the bonding is compared to one another, you can perform this test in the same way and then kind of categorize them, which one give you a better bonding strength than the other one. So that's more of the material property or coating property.
Yeah. Oh yeah. So yeah, thanks for clarifying. I agree. The bending does have to do with the hoop stress that we're experiencing, and then again, the adhesion is just kind of a spec that we are after.
Of course, the actual stress state in the cylinder is much more complex than just a simple tension, but there is a good component of that stress which is in tension.
Yeah.
That was very good presentation. I think you by now have something over 300, 400 slides of this work, and a good selected one was here. But you assume that most of us know what's going on, and you went right into the results. But yeah, upfront, definitely a good a few minutes needs to be spent on what are we talking about? Why cylinders are now being coated instead of using liner, which you kind of alluded to, but showing a cylinder would have helped up front.
Oh
yeah. And I'm not sure if we do have any images. I mean, this material that we received, the coating that we received, are proprietary information of Kamau Industry, which is a side industry working with Ford and Stellantis and other companies. Even the details of the coating is not revealed, but I'm not sure if there is any. You had some images or some videos showing or animations showing the coating, but if you could find one in the net, I mean, the first one, it shows this method in general. I'm not sure if it's the cylinder bore.
Okay.
The second one is a good animation of what's going on. I'm not sure what the third one is.
Oh, like it's just comparing like this one is coated and this one is not, and you can see the wear resistance. Kind of just selling the product, I guess.
Yeah.
But yeah, I agree. So I can add images from literature.
Yeah.
Or okay.
No, yeah, of course, yeah, from open sources, from literature. Oh, it doesn't have to be your own work. It's just for
reference. Okay.
Bringing everybody, up to speed in what is the problem. I mean, what is the technology? Why it's being done? It's a big part of what is known as circular economy. So any of these cylinders are damaged. We have many old cars in many parts of the world, not so much in North America, but other parts. So instead of making a new cylinder, you just take that cylinder and use 80% of that material and just recoat the inner of the cylinder because the rest of it is good, and then use it. So this is very big in Europe than what it is in North America. The mindset in North America is not remanufacturing, repair is just throw it away, buy a new one. But it's coming big time in terms of sustainability and energy resources and carbon footprint for that matter. So it's something very interesting that now all the companies are looking into. Of course, albeit that we are moving toward electric cars, but similar things would happen there as well. But for many parts of the world, this is still very much relevant and useful. And what she was trying to do in here was, first of all, better understand what is the adhesion mechanism. Despite what you would expect that there would be metallurgical bonding, because the temperatures are pretty high in this thermal spray, and not much thing else. It turned out to be mechanical interlocking, and that's why they are producing this surface treatments first to create this pattern, mainly for mechanical interlocking. And different wave shape and Kyocera shape is toward that. We do believe that cold spray will do a better job in here, but unfortunately,
I feel
we have to prove it before. But this was the first step it shed light, a great light, on what's going on in terms of this thermal spray, what are the characteristics, and what are the mechanism actually in terms of bonding, and also the she talked about the quasi-static. Also, the fatigue part is pretty interesting results associated with it, which shed a lot of light on what's going on and how the process can be optimized. As you can see, the amount of defects are really high in this process, but this is what currently is being done. I think Ford has most of their engines using this method, this technology, and other companies are just following the suit. So it's pretty becoming widely used in automotive industry. Yeah, very good presentation. I think you went over the most important things as far as characterization is concerned, and gotta time it well for the seminar you will have. You have half an hour. You will be selective, of course, because you will read your thesis in detail. We'll get there closer to the seminar day. Very well done.
Thank you.
Great job, Jessica.
Yeah, great job. Okay, I think. Oh, sure.
Oh, sorry, I'm not sharing anymore. But the as deposited sample obviously had a lot of variance in it, but it is machined after that. So they would deposit the coating, then they would subject it to either cutting or grinding and then honing. So that would produce, quite a uniform coating. And however, as we saw, it does induce quite a bit of residual stress, but it's necessary because we can't just use the coating as is. Yeah.
You had AFM microscopy for surface, right? I think.
Yes.
Yeah, I remember right now. Yes. I remember that.
Yes.
Okay, thank you. Thank you very much.
Thank you, everybody.
Thank you.
No, thank you, everyone, and have a good Friday.